Okay, hello everyone. Welcome back to another explained example from fluid mechanics. Today we're going to look at a problem from control volume analysis, specifically continuity or conservation of mass. So let's read the problem together. We have an incompressible fluid flowing past an impermeable flat plate, which is shown here, with the uniform inlet profile U equals to U naught. So that's the uniform flow. And a cubic polynomial exit profile. That's what we see here. And the profile is approximated as this function, where eta is y over delta. And the question is, find the flow rate Q across the top surface. So basically, we have an incoming flow and a flow that's leaving. Incoming flow is uniform. At this outlet, it's a cubic polynomial, and we want to find how much flow is going through this top surface, and the bottom surface is impermeable, so there's no flow, right? So this is a very classic example of a conservation of mass or continuity problem. Which requires us to first identify the control volume, which is shown to us, the dashed lines here that shows our control volume. So we have three control surfaces with flow going through them. This is the first one. I'm going to call this 1. And the normal to it is this vector. This is 2. And this is 3. Okay. So let's write down the continuity equation. It says that d dt of rho d volume over the control volume plus the flux over the control surface of rho v and dA has to be equal to 0. Here you have a steady problem, steady flow. There's no dependency on time. So this will be all 0. Basically, all we have to do is calculate this integral for all control surfaces, and they should all add up to 0, right? So we have CS1, the left plate or the left wall. We have CS2 and CS3. If you don't remember, rho is density here, v is velocity, the velocity vector, n is the vector that is perpendicular, the normal vector, normal to the control surface, and we're integrating over the area of that control surface. Okay. All right. So at the first surface inlet, v dot n is negative v, right? This is negative v. And it's scalar because you're doing a dot product. And that scalar is just u naught, right? So the velocity is opposite to the normal direction. So that's why it's negative, and its value is what we're calling u naught, right? And because it's constant over the area, you don't need to do the integration. It just becomes rho u naught, and it's negative, right? So again, v is a constant over the area, and it's just called u naught. It's the uniform flow, so we just pull it out of the integral. Okay. Plus rho v dot n dA at this on this surface, control surface 2. Okay, so here we're given this function for the velocity profile. And that profile is, we know it's a cubic polynomial. Well, first, what is v dot n? Well, v and n are in the same direction, so v dot n is just v, which is that velocity profile. But now the velocity profile is not constant, it's not uniform flow, so I can't just pull it out of the integral. I need to actually do the integration, right? So this second integral will be rho is a constant, but v dot n, which is equal to v, and v here, the horizontal velocity is this u profile. We need to integrate that. So u dA over control surface 2 plus rho integral of v dot n dA equals to 0. And note that this is just what we call the flow rate. So this is the Q that we're trying to find, right? So again, Q is defined as the integral, that's the flow rate, right? Q is v dot n dA over some area. So that is basically, if you multiply that by rho, that's the mass flux, the mass flow rate. That's what we have here. Okay. All right, so first thing I'm going to do, I'm going to divide everything by rho. Rho is a constant, it's incompressible flow. So I can just forget about the density, right? Okay, so we get negative u naught. Integral of dA is just A, right? So this is area 1 plus, now the integral of u dA. Now how do I integrate this velocity over the area? Well, I need to be able to express velocity in terms of the area, right? And let's write this velocity down here. U is some u naught times 3 eta over 2. Maybe I can write that as 3 over 2. Eta is this y over delta, and delta here is a constant, right? It's basically the thickness of this flow, the control volume you see here. Okay, so 3 over 2 y over delta minus y over delta cube divided by 2. Or maybe I can write it like this, y cube divided by 2 delta q. Okay, so this is our velocity profile at 2. Now, how do I relate this to area? Well, if you look at the third, if you imagine there's a third dimension here, right? All of this is going, it has some thickness, width into the paper, and that width into the paper is B. Okay, so there is a width here into the paper, which let's say it's B. Okay, so if I look at a tiny differential piece of the area, what is that going to be? Well, that can be expressed. Oops. See if I can get this right. Yeah, this strip of area that you see here, well, this is what we're calling B, right? The thickness, the width into the area, into the paper, sorry. This is B. So this is like basically dy, right? And of course, it's better if let me show this again. Starting from down here, this is our y. And let's say this is dy. Then this area, the highlighted area, is just b dy. So that's our dA, which is b dy, and dy is is basically the height of that tiny differential strip of area. Okay. Right, so why am I doing this? Because now dA, or area, is expressed in terms of dy, u is in terms of y, so now I would be able to integrate this. So if I go back down to our second integral and plug this in, we have the integral over area 2 of this term, which is u naught times 3 over 2 y over delta minus y cubed over delta cube divided by 2 right? Times dA. And dA, we just showed that it's just b dy. So I'm going to replace that by b dy. And you're integrating over y now. So y is going from 0 all the way to delta, right? This is our y. Y0 is this bottom wall. Y delta is the top surface where you have the flow rate. So that's our second integral. Okay, so that is the second integral. And lastly, this v dot n dA, we said that's just the q that we're trying to find. So these three terms together add up to 0. And remember, we just said rho is constant, so I can just get rid of it. I can just cancel it from all three terms because it's equal to 0. Okay. All right, so what are we trying to find? We're trying to find Q. And of course, everything here, this U naught is given to us. B is given to us. B is the width into the paper. Delta is also given to us. So we would want to find Q in terms of these parameter values, U naught, B, delta. We don't have any numbers in this problem. All right, so let's do that. Well, what is area 1? A1 here. Well, A1 is B times delta, right? Because here you have a rectangular inlet. Delta is the height, B is the width. So A1 is B delta. Okay. Now how about this integral? Okay, this integral is not very difficult. It's just a polynomial. First, we have the U naught, which is a constant. Then we have 3 over 2 y over delta. And y here, it's integral y dy. Okay, so let me do this first. We also have a b here. We have a u naught here. So I'm just going to pull those two out. Okay, now I have to integrate basically the 3 over 2 y over delta. And that is y squared divided by 2 delta. So that's the first term. Then I have y cubed divided by 2 delta cubed. And that is y to the 4th divided by 8 delta q. And this is going from y0 to y delta plus q, which is our unknown. Okay, we're almost there. So I have negative u naught b delta plus u naught b. Now I just need to evaluate this from 0 to delta. If I plug in 0, all the terms will be 0. So we really just need this upper bound delta. So I just need to plug in instead of y delta. And that is 3 over 2. And 2 is multiplied by 2. So that's 3 over 4. Delta squared over delta, which is just delta, minus delta to the 4th divided by delta cube, which is just delta divided by 8. And this is, of course, 6 over 8 minus 1 over 8 delta. So that's just 5 over 8. And so finally, I can just find Q to be U naught B times delta if I take these two terms to the other side, minus 5 over 8 delta, which is 3 over 8 B delta U naught, and that is our final answer. Okay, so this is a pretty good example for continuity, conservation of mass. in a control volume. Of course, it's an interesting problem because you have non-uniform flow at one of the outlets, right? And you can also, we'll also soon look at a problem where you have non-uniform flow and you want to apply conservation of momentum to, for example, find a force. For example, like what's the drag force acting on the wall, or how much force you need to keep something in place, those types of problems. But for now, this is our conservation of mass problem, and soon we'll look at a conservation of momentum problem. Thank you, and let me know if you have any problems, if you have any questions.